Namaste students, welcome back to my channel. I hope you all are fine at your home. In our previous video, we have studied about the two chemical properties of the 15th group element. Those two chemical properties are the oxidation state exhibited by the 15th group element and the reactivity of the 15th group element towards hydrogen. Now, in this video, we'll learn about the remaining chemical properties of 15th group element, and we'll also talk about the anomalous behavior of the nitrogen. So, let's get started. Study the third chemical properties of 15th group element, and that is reactivity towards oxygen. The first member of this family, that is nitrogen, we all know that it is an electronegative element. Due to its electronegative property and a strong affinity to form p-pi bond with the oxygen, nitrogen forms a number of oxides of oxidation state ranging from +1 to +5. Nitrogen reacts with oxygen very easily. Why? Because of its electronegativity and tendency to form p-pi bond and form a number of oxides of oxidation state ranging from +1 to +5. But the other elements of this group, due to less electronegativity and less tendency to form p-pi bond with the oxygen, they form only limited oxides when react with oxygen of the oxidation state ranging of +3 and +5. It means nitrogen will form 5 oxides when reacts with oxygen. These 5 oxides are N2O, NO, N2O3, N2O4 and N2O5. In N2O, the oxidation state is +1, here it is +2, here it is +3, here it is +4 and here it is +5. So because of its electronegativity and tendency to form p-pi bond with the oxygen, it forms a number of oxides with oxygen ranging from +1 to +5. But if I talk about phosphorus, phosphorus form P4O6, P4O8 and P4O10. In P4O6, its oxidation state is +3. In this it is +4 and in this it is +5. So phosphorus along with +3 and +4 also form an oxide in which the oxidation state is +4. But if I talk about arsenic, it forms As4O6 and As4O10. Similarly, antimony, it forms Sb4O6 and Sb4O10. And the bismuth form Bi2O3. Clear? So nitrogen form 5 oxides, +1, +2, +3, +4, +5 oxidation state. Phosphorus forms 3 oxides, arsenic and antimony forms 2 oxides, whereas bismuth form only 1 oxide. Why it is so? Because on moving down the group, first of all, electronegativity decreases, and second thing, tendency to form p-pi bond also decreases. As a result of which, bismuth form only 1 oxide when it reacts with the oxygen. Now, if I talk about the acidic strength, of these oxides, then with increase in the electronegativity of the central atom, acidic character increases. Clear? With increase in the electronegativity of the central metal atom, acidic character increases. For example, if I talk about N2O3, P4O6, As4O6, Sb4O6 and Bi2O3. In all these oxides, the oxidation state of the central atom is +3, and we know that on moving down the group, electronegativity decreases. So if we have to arrange these oxides, I'm talking about these oxides. because in these oxides the oxidation state is +3. So if we have to arrange these oxides in the increasing order of their acidic character, so with increase in the electronegativity, acidic strength increases. It means most acidic is this one and least acidic is this one, because this one is most electronegative and this one is least electronegative. So the acidic strength becomes N2O3, P4O6, AS4O6, SB4O6, and the least one is Bi2O3. So if we have oxides in which the oxidation state of the central atom is same, then we'll arrange those oxides in the increasing or decreasing order of acidic strength by seeing their electronegativity strength. Greater the electronegativity of the central atom, greater is the acidic strength. But suppose if we have to arrange the oxides of one atom, means oxides of a single atom. For example, I have to arrange these oxides in the increasing order of their acidic strength or decreasing order of their acidic strength. So with increase in the oxidation number, electronegativity increases, and if electronegativity increases, acidic strength increases. Clear? With increase in the oxidation state, oxidation number, electronegativity increases. Means out of these five, this nitrogen is most electronegative, whereas this one is the least electronegative. So this one is acidic and this one is least acidic. So the arrangement is N2O5, N2O4, N2O3, NO, N2O. So when we have to arrange the oxide of a single element, then we'll see the oxidation state of that element. In the oxide which has higher oxidation state, that oxide is more acidic, whereas the other one are less acidic. But if we have to see the oxides of different elements of the same group, then we have to see the electronegativity of the atoms. So in this we are seeing the electronegativity of the atoms. Nitrogen is most electronegative, that's why it is more acidic, and Bi is least electronegative, that's why it is least acidic. In this we are seeing the oxidation state in the particular atom. So this is the reactivity towards oxygen. Now we'll study the reactivity towards halogen. Now, when the elements of 15th group reacts with halogen, they form two types of halides. Trihalides and pentahalides. They form two types of halides, trihalides and pentahalides. And in our previous video, we studied that nitrogen can extend its covalency maximum up to +4. It means in case of nitrogen, we didn't get pentahalides. We get only trihalides. So the elements of group 15 form two types of halides. These halides are trihalides and pentahalides. First of all, we'll talk about trihalides. Now, the members of 15th group, they react with halogen to form trihalides having general formula EX3. And if we talk about the hybridization is same that we have studied in the hydrides, in the trihydrides. In this also the hybridization of the central metal atom is sp3 and the shape is pyramidal. Clear? The members of 15th group reacts with halogen to form trihalides having general formula EX3. In these trihalides, the central atom undergoes sp3 hybridization and the shape becomes pyramidal. Now, if I talk about the bond angle, if you remember in trihydrides, we studied that bond angle decreases on moving down the group. But in this case, the case is different. In trihydrides, the central atom is changing, but the hydrogen remains same. In this case, we are going to change the halogen atom because we have different halogen atoms. So we are going to change halogen atom. Suppose I have NF3, NCl3, NBr3 and Ni3. And my question is to arrange these trihalides in increasing bond angle order. I have to arrange these trihalides in increasing bond angle order. So if I talk about the halogens have the tendency to take electron, means halogens are electronegative elements. Greater the electronegativity of the halogen atom, smaller is the bond angle. What I am saying, greater the electronegativity of halogen atom, smaller is the bond angle. Now, why I am saying this? If I take these two, NF3 and Ni3, the structure of NF3 is like this: F, and a bond in lone pair. Ni3 is also same: I, and a lone pair. Now, fluorine is more electronegative than iodine. So, fluorine attracts the shared pair of electron towards itself. As a result of which the electron cloud around the nitrogen decreases. And due to the decrease in the electron cloud, the two bonds come close to each other, as a result of which bond angle decreases. But in this case, nitrogen is more electronegative than iodine, so the electron will shift towards nitrogen, as a result of which the electron cloud around the nitrogen increases, and due to the increase in the electron cloud, there is a repulsion between the bond pair, as a result of which bond angle increases. So, greater the electronegativity of the halogen atom, smaller is the bond angle. So, with increase in the electronegativity of the halogen, bond angle decreases. Clear? In trihydride, the concept is different. In trihalides, the concept is different. In trihalides, with increase in the electronegativity of the halogen atom, our bond angle decreases. So, trihalide structure, formula, hybridization, structure, and the bond angle. Properties of trihalides. We will study the properties of trihalides. Now, all the trihalides are predominantly covalent. Mostly trihalides are predominantly covalent, and the ionic character increases down the group, as a result of which BiF3 and SbF3 are ionic, whereas rest are covalent in nature. So first of all, trihalides are predominantly covalent in nature, and down the group ionic character increases, as a result of which BiF3 and SbF3 are ionic in nature, while all other members are covalent in nature. Now, second, if I talk about the stability of the trihalides, the trihalides of nitrogen are least stable. But if I talk about NF3, due to strong NF bond, it is an exothermic compound and hence it is stable. though the halides of nitrogen, the trihalides of nitrogen are least stable, but due to strong NF bond, it is an exothermic compound and hence is a stable compound, and it is so much stable that it do not undergo hydrolysis even with water or dilute acid or alkali. So due to strong NF bond, it acts as an exothermic compound. It is an exothermic compound, and being an exothermic compound, it is stable compound. If I talk about NCl3, NCl3 acts as an explosive and it also undergo hydrolysis to form NH3 and HOCl. So NCl3 acts as an explosive and it undergo hydrolysis to give NH3 and HOCl. If I talk about NBr3 and Ni3, then these two occur in the form of unstable ammoniates. These occur in the form of unstable ammoniates. Unstable ammoniates having formula NBr3 dot NH3 and 3Ni3 dot NH3. This is the unstable ammoniate of bromine, and this one is the unstable ammoniate of iodine. Now, if I talk about this one is stable in its moist state, but in dry state, it acts as a mild and harmless explosive. Ammoniates of Ni3 in the moist state is stable, but in the dry state, it acts as a harmless and mild explosive, and when it is in dry state, it undergoes decomposition to give N2 plus I2 plus NH4I. N2 plus I2 plus NH4I. So these are the trihalides of nitrogen. Trihalides of nitrogen are least stable, but NF3 is stable due to strong NF bond and its exothermic nature, and because of its stability, it do not undergo hydrolysis even with the water or dilute acid. But if I talk about NCl3 acts as an explosive and it undergoes hydrolysis to form NH3 and HOCl. NBr3 and Ni3 exist as an unstable ammoniates, and if I talk about Ni3 ammoniate, then that ammoniate is stable in the moist state but act as a mild and harmless explosive in the dry state. Now, if we talk about the stability of these trihalides, on moving down the group, the stability of the trihalides decreases. And the decrease in the stability of the trihalides as we move from NF3 to Ni3 is the bond present between the nitrogen and the halogen. On moving down the group, the bond present between the nitrogen and the halogen decreases and bond strength decreases, and due to the decrease in the bond strength, its stability also decreases. Now we'll talk about hydrolysis. Third, we'll talk about hydrolysis. Now we already studied that NF3, because of its stable nature, do not undergo hydrolysis. So NF3 do not undergo hydrolysis. Now if I talk about NCl3, we studied that it undergo hydrolysis to form NH3 plus HOCl. Then if I talk about PCl3 also undergoes hydrolysis to form H3PO3 plus HCl. PCl3 undergo hydrolysis to form H3PO3 plus HCl. Similarly, AsCl3 undergoes hydrolysis to form H3AsO3 plus HCl, same as that of the phosphorus. The E is same as that of the phosphorus. Next one, SbCl3 reacts with H2O to form SbOCl plus HCl, that is antimony oxychloride, and here the reaction is reversible reaction. Similarly, BiCl3 also undergoes hydrolysis to form BiOCl plus HCl. So it is clear from these 5 reactions that as we move from nitrogen to bismuth, the ease of hydrolysis decreases. Because this reaction is very fast reaction, it rapidly undergo hydrolysis to form NH3 plus HOCl. Similarly, if we talk about PCl3, the reaction is not so fast as compared to NCl3, but still it is faster. And as we move down the group, here the reaction are reversible. Reaction reversible means after some time the product get converted into the reactant. So the ease of hydrolysis, if I talk about the ease of hydrolysis decreases as we move from nitrogen to bismuth. Clear? Now next we'll talk about the next property, that is Lewis acid and base character. Lewis acid and base character. Now in others we are studying only about Lewis acid or Lewis base, but in this I am talking about both Lewis and base character. Means we will going to study both Lewis acid and base character. Now the reason behind this is, if I talk about the trihalides of nitrogen family, its structure is pyramidal. Pyramidal structure means it has a lone pair, so it has the tendency to donate the lone pair. But if I talk about the other members of this family other than the nitrogen, means remaining members of the family other than the nitrogen, they also have lone pair of electron, but with the lone pair of electron they have vacant d orbitals also, and because of this they can easily accept the electron. So in the trihalides of this family, we found two tendency. One is the donating tendency and second one is the accepting tendency, means acceptance of electron or donation of electron. If we talk about the fluorides and chlorides of phosphorus, arsenic and antimony, if we talk about fluorides and chlorides of phosphorus, arsenic and antimony, then these trifluorides accept the electron in their d orbitals and thus act as a Lewis acid. Accept the electron in the d orbitals and thus act as a Lewis acid. Now if I talk about the acidic strength, if I talk about the acidic character, means how easily Lewis acid character, how easily they accept the electron. If I talk about PF3, ASF3 and SbF3. Now phosphorus is more electronegative than AS is more electronegative than Sb, so phosphorus can easily attract the electron in its d orbital, so the acidic character is like this. Means this one act as a strong Lewis acid and this one act as a weak Lewis acid. But if I talk about PF3, PCl3 and PBr3, means central atom remains same but I am changing the halogen. So with increase in the electronegativity of the halogen, its tendency to attract electron increases, because electron attract the shared pair of electron towards itself, as a result of which the electron density at that particular central atom decreases, and due to the decrease in the electron density it easily attract the electron from the outside. So the acidic character like this. So if I talk about the fluorides and chlorides of phosphorus, arsenic and antimony, they act as a Lewis acid because of their tendency to attract the electron, to accept the electron in their empty d orbital. But if I talk about the halides of nitrogen, then the halides of nitrogen act as a Lewis base because they have the tendency to donate electron, they don't have the tendency to accept electron. So the halides of nitrogen behave as Lewis base. Halides of nitrogen behave as Lewis base, and similarly in this case, with increase in the electronegativity of the halogen atom, the Lewis basic character, with increase in the electronegativity of the halogen atom, Lewis base character decreases. Why? Because fluorine attract the shared pair of electron towards itself, as a result of which the electron cloud around the nitrogen decreases, so it will not donate the electron. It will be difficult for the nitrogen to donate electron. But if I talk about Ni3, in Ni3 the electron cloud is near the nitrogen atom, as a result of which the density is very high, so nitrogen atom can easily donate its electron to any other species. So with increase in the electronegativity of the halogen, Lewis basic character decreases. So the least basic is NF3 and the most basic is Ni3. Clear? Lewis base and Lewis acid character, fluorides and chlorides of phosphorus, arsenic and antimony, they act as Lewis acid. Why they act as a Lewis acid? Because they have vacant d orbital, so they can easily accept the electron in those vacant d orbitals. And halide of nitrogen act as a Lewis base. Why it act as a Lewis base? Because it has a lone pair and it can donate the lone pair, but with increase in the electronegativity of the halogen, it becomes difficult for the nitrogen atom to donate the lone pair of electron. So these are the properties of trihalides. Now we'll study the next type of halide formed by the 15th group element, and those halides are pentahalides. Those halides are pentahalides. Pentahalides. Now pentahalides, these pentahalides have general formula EX5. Pentahalides have general formula EX5 and the hybridization is sp3d and the shape is trigonal bipyramidal or triangular bipyramidal. Clear? Pentahalides, general formula EX5, sp3d hybridization and the shape is trigonal bipyramidal. Now if we talk about the nature or the stability, now pentahalides are less stable as compared to the trihalides. Pentahalides of this group are less stable than trihalides. Now the reason behind this is inert pair effect. Due to the inability of the s electron to participate in bond formation, pentahalides are less stable as compared to the trihalides. And because of this, if we talk about phosphorus, in phosphorus we get PF5, PCl5, PBr5 and Pi5. Means fluoride, chloride, bromide and iodide of phosphorus are stable. But if I talk about arsenic, antimony and bismuth, Fi5 is also not stable. Fluoride, chloride and bromide of phosphorus is present. Now if I talk about arsenic fluoride is also present, arsenic chloride is also present. Now bromide of arsenic is not stable. Similarly SbF3 is also present, but in case of BiF3 is also present. Means if we talk about the fluoride, fluoride of phosphorus, arsenic, antimony and bismuth are stable. Pentafluorides of phosphorus, arsenic, antimony and bismuth are stable. If we talk about chloride of phosphorus, arsenic and antimony are stable. If I talk about bromide of only phosphorus is stable and iodide of even not the phosphorus is stable. Clear? We are talking that pentahalides are less stable than trihalides. And because of this reason, fluorides, pentafluoride of phosphorus, arsenic, antimony and bismuth we have. means the stable fluorides we have. Chlorides we have, stable chlorides we have only of phosphorus, arsenic and antimony. Stable bromides we have only of phosphorus, and iodide, pentaiodide of any element, 15th group element, is not at all stable. It means if I talk about +5 oxidation state, in case of bismuth, only BiF5 is the stable compound. And all these compounds are covalent in nature. All these compounds are covalent in nature. Now, if I talk about the preparation of these compounds, so suppose I have As4O10, that is the oxide of arsenic. When I react this with F2, then it gives AsF5 plus O2. Similarly, SbO4 on reacting with fluorine, it gives SbF5 plus O2, and PCl3 reacts with Cl2 to form PCl5. PCl3 reacts with Cl2 to form PCl5. Similarly, PCl5 on reacting with AsF3 gives PF5 plus AsCl3. So in this way we can able to prepare the pentahalides. So what we have studied in pentahalides, first of all the formula, second one the hybridization, third one the shape. Next, in properties we have studied that pentahalides are less stable than trihalides due to inert pair effect, and because of this reason the fluorides, pentafluorides of phosphorus, arsenic, antimony and bismuth we have. But if we talk about pentachlorides, the stable pentachlorides of only phosphorus, arsenic and antimony we have. The stable pentabromides we have only of phosphorus, and we don't have any stable pentaiodide of these compounds. We can prepare these compounds with the help of this. Now PCl5, because in PCl5 the oxidation state of phosphorus is +5, and in PCl3 the oxidation state of phosphorus is +3, and +3 is more stable oxidation state as compared to +5. So PCl5, because of its instability, it acts as a good reducing agent. PCl5 being unstable, it acts as a good reducing agent. Now there is a question that why PCl5 acts as a good reducing agent. So the reason behind this is due to instability, PCl5 act as a good reducing agent. And why it is unstable? Because it get converted into PCl3 plus Cl2. In PCl3 the oxidation state is good reducing agent or chlorinating agent, because it can easily provide us chlorine, because +3 oxidation state is more stable than the +5, so it readily decomposes to give PCl3 and chlorine, and because of the presence of the chlorine it acts as a good chlorinating agent. So because of its instability it acts as a good reducing agent. Now if we talk about in vapor phase, PCl5 acts as a covalent compound. PCl5 acts as a covalent compound in vapor state. But if I talk about in solid state, PCl5 acts as PCl4 positive and PCl6 negative. So in this way PCl5 exists in the solid state. Means in solid state it exists in the form of ionic compounds, whereas in the vapor state it present in the covalent form. If I talk about PBr5 and Pi3 in the solid state, PBr5 and Ti3 in the solid state they also exist as PBr4 positive, Br negative, and Pi4 positive, I negative in the solid state. So PCl5 act as a good chlorinating agent. Why PCl5 act as a good chlorinating agent? Because of its less stability. It readily get converted into PCl3 and give us chlorine. That's why it is a good chlorinating agent. And if I talk about the existence of PCl5 in the vapor state, it act as a or exist as a covalent compound, whereas in the solid state it exists as ionic compound PCl4 positive and PCl6 negative. Similarly, PBr5 and PI5 also exist as a covalent compound in their vapor phase, but in the solid phase they exist as PBr4 positive Br negative and PI4 positive I negative. So these are the properties of pentahalides. So our chemical properties of group 15 element is done. Now we'll talk about the anomalous behavior of nitrogen. That is why nitrogen behave anomalously differently from the other elements. Even when all the elements are present in the same group and all the elements have same electronic configuration. So why the properties of nitrogen are little bit different from the other elements. Nitrogen. That is why nitrogen behave differently as compared to other elements. The reason behind this is, first one, its small size. The size of the nitrogen is very small as compared to the other elements. Second one, its electronegativity. Nitrogen is highly electronegative as compared to the other one. Third one is the absence of d orbital. Means in other elements we have vacant d orbital, but in nitrogen we don't have vacant d orbital. And fourth one, because of its high ionization enthalpy. So because of these four reasons, nitrogen behave differently from the other elements. What are these reasons? I'm repeating again. First one, the size. The size of the nitrogen is very small as compared to the other element. Second one, its electronegativity. It has very high electronegativity as compared to the other one. Third one, absence of d orbital in the nitrogen, whereas the presence of d orbital in other elements. And fourth one is it high ionization enthalpy. Now, because of these four reasons, what different properties nitrogen show? First one is the state. If I talk about N2, N2 is gaseous at room temperature. If I talk about N2 is gaseous at room temperature. Why? Because of weak van der Waals force of attraction. Due to small molecular mass of nitrogen, the nitrogen molecules are held together by weak van der Waals force of attraction, and because of this they are gaseous at room temperature. But if we talk about the molecules of phosphorus, arsenic and antimony, they exist as a solid at room temperature. Why they exist as a solid at room temperature? Due to strong van der Waals force of attraction. So due to strong van der Waals due to a high molecular mass, they held together by strong van der Waals force of attraction. Hence they are solid at room temperature. Whereas due to low molecular mass, due to small molecular mass, it held together by weak van der Waals force of attraction and hence gaseous at room temperature. If I talk about bismuth is present in its metallic form in the elemental state. It is present in the form of elemental state and held together by the metallic bond. This is the first anomalous behavior. Second one, tendency to form multiple bonds. Now, due to very small size and high electronegativity, nitrogen has a strong affinity to form p-pi bond with other elements as well as with itself. Means if I talk about two nitrogen in between two nitrogen, we have 3 bonds, means we have multiple bonds. But if I talk about phosphorus, in phosphorus we don't have multiple bond, we have a single bond. Similarly, in arsenic also we have single bond. So because of its small size and high electronegativity, nitrogen has a strong affinity to form p pi multiple bond with itself as well as with the other element. That's why N2, in between N2 we have 3 covalent bonds, but in case of phosphorus we have single covalent bond, and it exists in the form of P4 molecule, AS4 molecule and Sb4 molecules. Now next, if I talk about catenation. Now due to inter-electronic repulsion, the catenation property of nitrogen is very less, means it can combine with its molecule only up to number 3, means only 3 atoms of nitrogen can combine to form a compound. After that, the inter-electronic repulsion is so large that they can not able to combine with each other, and the ion which we get is known as azide ion, that is N3 negative. Clear? In this we get N double bond N negative, positive and negative. This is the formula of the azide ion. So because of inter-electronic repulsion, the property of catenation is very less in the nitrogen, and only 3 atoms of nitrogen can combine to form a molecule. After that, the atoms of nitrogen cannot able to combine with each other. In this group, the maximum catenation power is present in phosphorus. So phosphorus have maximum catenation tendency. And as we move down the group, due to the increase in the size, the catenation tendency goes on decreasing. Now, if I talk about reactivity, due to 3 covalent bond present between the nitrogen is inert. Due to 3 covalent bond between nitrogen, N2 is inert, but phosphorus is highly reactive, and as we move down the group, reactivity goes on decreasing. It means the highly reactive element of this group is phosphorus. Clear? Otherwise, what is the trend? That on moving down the group, reactivity decreases, but due to inter-electronic repulsion or due to the presence of multiple bonds, nitrogen behave as an inert substance, inert gas, and phosphorus act as a highly reactive element of group 15. So these are the anomalous properties of nitrogen, and these properties are due to the absence of d orbital, high electronegativity, large ionization enthalpy, and small size. So students, that's all for today. I hope you have learned a lot of things from this video. I'll see you soon in my next video.